Okay, so that's kind of how we set the test up. And what I thought I'd do is just draw some stress-strain curves for different types of materials and define some of the parameters, beyond just the Young's modulus, and show you some of the differences in the types of behavior. So we'll start with metals. And if I draw the stress-strain curve for sort of a typical metal, it would look something like this. So I'll draw the curve, and then we'll go through the different parameters that define it. So there's stress, there's strain. So as we've been talking about, there's a linear elastic part to it. So the stress and the strain are just linearly related. And then at some point, the deformation becomes irrecoverable, and that's called plastic deformation. And then the response is nonlinear. So then the response would look something like that. And then at some point over here, your specimen would fracture. Okay?
Did you draw it going up and then back down on purpose? Or just
I did. I draw it up and back down. So the question was, did I draw it up and back down on purpose? And I did draw it up and back down on purpose, because that's what they often look like. Okay. Okay, so the slope here is our Young's modulus. And let me write down some characteristic features here. So we've already talked about Young's modulus quite a bit. So that characterizes the initial linear elasticity. Then there's some point at which the stress-strain curve becomes nonlinear, and sometimes it's difficult to figure out exactly where that point is. You'd kind of like to know where that point is. And there's kind of a way of doing it that gives you a sort of consistent way, and it's called the 0.2% offset yield strength. So the 0.2% offset refers to the fact that if you load it up to that stress and then you unload it, you've got 0.2% plastic strain. And remember, we said that when we had elastic deformation, if I load up in the elastic regime and then I unload, I just go back down along the same slope. Right? So if I go up to this yield strength, say it's up here somewhere, so it's just become nonlinear. If I unloaded it, the unloading occurs parallel to my slope of my loading curve there. It's parallel to the Young's modulus there. And then this little bit of strain here, there's a little bit of offset. That's my plastic strain, my permanent strain. That strain is 0.2% or 0.002. And the stress that corresponds to that is called our 0.2% offset yield strength. And I'm just going to write sigma y because I'm realizing I haven't left myself enough room to write 0.2% offset yield strength. So I'll just call that sigma y over here. Okay? So you load it up, you unload it, and when this permanent plastic strain is 0.2%, the stress that that corresponds to is your 0.2% offset yield strength. And that permanent deformation is called plastic deformation. So another characteristic of a lot of metals is that they're ductile, and that means you can deform them to very large strains. So I'll come back and talk about how we can characterize that ductility. This belongs in that pile there. But let me show you one of the specimens that was from the lab yesterday. So this is a brass specimen here. So it started out this big here, and when it was deformed and failed, you can kind of see where it failed here, it was that length there. So you can see just looking at those two pieces that it's got longer by about 25 millimeters, something like that. So that's a measure of the ductility, how much longer it got before it broke. Okay? So let me pass those guys around. And you've seen all this before. You don't need to see it. But you can look if you want. So let me just pass those around so you can kind of see, you know, you can compare the lengths of those and you can kind of see how it's failed. Okay? Okay. So let me write down one more thing here. So if I go from here over to the left, I've got linear elastic deformation. And if I go from there, say there, over to the right, I've got plastic deformation. So that's the permanent deformation. So I want to talk a little bit more about the plastic strain. So say I draw my curve again. And say this time I have my linear elastic part, and then I don't load it right until fracture, but I just load it partly into the plastic regime there. So I'm not going to fracture it. I'm just going to load it partly up there. And then if I unloaded it, it would unload with the same slope as my Young's modulus here. So if I unload this, try and make it the same there, it would unload like that. Okay, so say that slope there is E, that slope there would also be E. Okay, so when we unload it, we've got this amount of the plastic strain, so that would be our plastic strain there. Okay, so that's permanent. You can't recover that. But you do recover the elastic strain. Okay. So if I unload it, I come down here. If I then reload it again, I would go back up that same line with the same slope as E. So if I reloaded it, I would go back up there, and then in fact I would pick up over here, and the curve would just continue. So if I unload it, I come down on this line with a slope of E because I'm recovering that elastic deformation that's associated with that. If I reload it, I go back up there, and then I kind of pick up the curve where I left off. Okay? Okay, so we're good so far? It's all just kind of definitions. Another definition is strain hardening. So let me draw the curve again. Here's stress and strain. So here's my linear elastic bit again. And then if the curve does this, it's called strain hardening. That refers to if the strain increases and the stress is increasing with strain in the plastic regime, that's strain hardening. And there's another thing called strain softening, which is the opposite. So there's my stress-strain curve again. Say the linear elastic bit was here, and then it did something like that. This would be strain softening here. Oops. stress decreases there. Okay, so that's strain hardening and strain softening. So just more definitions. And there's a couple of other definitions here. The maximum value of the tensile strength is called the ultimate tensile strength. So that maximum value there is the ultimate tensile strength, sigma UTS. And then the last thing is something called the ductility. And the ductility is if we went out to the fracture point here, and then we unloaded it back along our slope of E, then this total plastic strain here would be a measure of how ductile the metal was. Let me make another little drawing with that, because that one's getting a little crowded. So that would be the strain to failure, so let's call that epsilon F. And that's a measure of the ductility. Okay, so that's the total amount of plastic strain you would have at fracture. Okay. Yes? On the epsilon? Yeah. So the question is, what's the subscript on the epsilon? It's epsilon F for a final fracture, one of those F words. Okay, is everybody else okay? All right, so a lot of this is just sort of definitions. Another kind of behavior that you see in metals and sometimes in polymers is that as you pull on them, the plastic deformation becomes localized in one spot, and the fracture eventually happens at that localized spot. So here's my wasted cylinder here, and I'll pass this around too so you can kind of see it. So here's the wasted bit here, but if you look at it carefully, the diameter right where it's failed is much less than that. And that's called necking because it's narrow, like a neck. And so that necking is a localized type of failure, and the plastic deformation has localized there. Here you go, Simona, you can look at that. So Simona Socrate here is a faculty member in, well, I guess you're a research scientist in mechanical engineering, and she teaches similar courses like this. And she's helping me with the MIT X version of this. So she's very, very helpful about that. So the idea is with the necking is that you may have one cross section that's a little smaller than another, and in that section the stress will increase, and as the stress increases, the strain increases, and as the strain increases, the area gets smaller again, and it's sort of an instability. The more the stress increases, the more the area gets smaller, and that's really what causes the localization. And so it eventually leads to this, this fracture. So we can say as we pull on some materials, so this especially happens in ductile metals. The plastic deformation becomes localized. So one section, one cross section may be weaker or have a smaller area. And then the stress at that section increases. So if the stress increases, then the strain increases. And then the area gets smaller again. And eventually this leads to fracture. So I can draw a little sketch of what happens here. So say this was our original wasted section, and then we'll have some even narrower piece here, and that'll, oops, that'll lead to fracture there. So this is the neck here and the fracture. Okay, so the cylinder, the wasted cylinder that's going around, can you see the neck and the fracture, whoever's got it?